I'm here with Nate Radcliffe. Nate, you gave a great talk in a symposium today. Let me get you just to outline what the subject matter was, and then I already know I have some follow-up questions.
So I was asked to speak on corneal biomechanics and whether corneal biomechanical assessment provides any additional information in the management of glaucoma. Now, as you know, corneal thickness has been a great field for us to learn a lot more about the management of our glaucoma patients. We initially were interested in corneal thickness because we thought we might adjust pressure measurements based on the thickness, and ended up learning in the ocular hypertension treatment study that having a thin cornea is an independent risk factor for glaucoma progression.
Meaning that even when we adjusted for the IOP based on corneal thickness, thin corneas still carried an additional risk factor.
That's right. And I think that where we are today with corneal thickness is we don't so much rely on it to adjust a pressure number, but rather we just know that someone who has a thin cornea is indeed at a higher risk for both the development of glaucoma and for its progression.
But your talk today dealt with more than just corneal thickness. What did you talk about?
Right. So I spoke about corneal biomechanical properties, and probably the most applicable thing that we have right now is corneal hysteresis. Now, corneal hysteresis is defined as and this is using a technique called air puff tonometry, where we look at the pressure at which the cornea bends in and the pressure at which it rebounds and forms its regular shape. And it turns out there's a difference between those two pressures. In some eyes, there's a small difference, and in some eyes, there's a large difference. That difference is defined as corneal hysteresis. It is thought to be a measure of corneal viscous dampening. So I think of it as how well can this cornea function as a shock absorber. You can imagine that some corneas are very strong and can take a lot of energy without having much of a movement in the cornea, and others will bend with just the slightest amount of pressure.
Now, I have a sort of complicated question here. Complicated for me, not for you, Nate. Now, I can understand why it is that a thin cornea might influence the IOP measurement, and that's going to play into risks, and maybe it's a marker for something else. We don't know what. Hysteresis is, I would guess, is not going to play a substantial role in the way that I'm measuring pressure. Is it that hysteresis at the cornea is a marker for hysteresis at the lamina?
Well, that's one of the theories, and it is very complex. And in fact, hysteresis does influence our assessment of the pressure as well. A couple of things about hysteresis, and I'll talk a little bit about the corneal thickness and hysteresis because they are related. They're weakly correlated to each other. But when the pressure comes up in an eye, the hysteresis drops. So it is more of a corneal behavior than an intrinsic corneal property, and it's also more dynamic. For example, corneal thickness is often symmetric. Corneal hysteresis is often asymmetric. In fact, it's been shown that it'll be lower in the eye with the worst glaucoma damage. So it's more dynamic, more adaptive to the pressure. But if you have glaucoma damage, even if you lower the pressure, the hysteresis will come up a little bit, but still stay very low. So it is also a sign of how much glaucoma damage an eye has accumulated. And as a side note, patients with keratoconus also have a lower corneal hysteresis as well.
Interesting stuff. So you're saying that even in patients with symmetric pressures, that there can, and symmetric CCTs, there can be differences in hysteresis between right and left eye.
Yep, and those differences will correlate to glaucoma stage, visual field damage. I mean, it's fascinating to me that and the mean deviation of a visual field is often very closely correlated with a corneal hysteresis. And it's, in my mind, the fact that the cornea, bouncing air off a cornea, is going to tell you something about a patient's visual function related to glaucoma is fascinating, and I can't explain fully why that's the case, but I think it's something we need to pay attention to and learn more about.
Now, Nate, I'm a numbers guy. I would love to measure this parameter. How do I do it?
So currently, we have one device that's the ocular response analyzer created by Reichert, and it's a pneumotonometer, or an air puff non-contact tonometer is the correct term. And so you can use it to measure the pressure and the corneal hysteresis. So it's very simple. It's similar to an autorefractor. The patient sits down, you get a measurement very quickly. It will give you something called a corneal compensated intraocular pressure, which is a pressure adjusted for hysteresis. It can be useful, but in my mind, I still like to keep them separately, as I think these adjustments make things a little simpler than they need to be. So you measure that, and to give you an example, probably the average patient is around 9.5. 9, 8, 7, 6 are more lower numbers, and often someone with a hysteresis of 5 has a decent probability of having glaucoma. On the other side of things, these high hysteresis numbers can suggest, just as a thick cornea would, that you might not need to be as concerned about a high pressure number in those patients. So there is an immediate clinical usefulness. One other thing is that patients with high hysteresis don't show much of a change in their pressure when they're given eye drops or have laser trabeculoplasty. And patients with a low hysteresis have more of a response.
That's really interesting.
It is, and in fact, it's paradoxical, because as we were saying, low hysteresis means you've got worse prognosis in terms of glaucoma progression, but at the same time, I put you on a drop, and you will probably get a 30% pressure reduction from a prostaglandin analog, whereas that person with the low risk but high hysteresis may show a more modest response. For me, the implications are huge, because I don't want to overtreat my high hysteresis patients who may have a pressure of 24 but a full field healthy nerve. I can put them on a drop and feel comfortable that I didn't need to get such a pressure reduction. And meanwhile, I won't pat myself on the back when I get 30% pressure reduction in a high-risk, low hysteresis patient. Instead, I'll monitor them carefully and even consider adding therapy.
Really, really cool stuff. Yep. Nate, thank you very much for spending time with us today.
Thank you very much, Josh. Good to see you always.